One more time, we will take a look at the concave up, concave down, and points of inflection of a function. This one happens to be a quotient. We'll need to use quotient rule to find the derivative and then the second derivative. So we have f, we have g, we have f prime being 3 and g prime being 1. Quotient rule, f prime g minus g prime f divided by g squared. F prime is there. G minus g prime f over g squared. Simplify things as much as we can. Distribute the 3x. And we have two like terms on top. There's your first derivative. Second derivative, now we have f and g. F prime is 0. G prime, we need to use the chain rule. 2 comes down, x minus 3, exponent of 1, multiplied by a derivative of the bracket. So we have 2x minus 6. Second derivative, f prime g minus g prime f all over g squared. First term cancels off to 0. Second term works to 18x minus 54. Bottom we can work to x minus 3 to the power of 4. And now we need to look to factor the top. What's common to both 18x and 54? Actually, we can take out a full 18. Which is highly advantageous. Leaves us with an x minus 3 that we can cancel with the bottom. Leaving our second derivative like so. Now, just like with the first derivative test, we can't deal with this type of function, this quotient, by just setting equal to 0 and going on. We need to look at it independently, determine what's going to make the top work out to 0, what's going to make the bottom work out to 0. Well, the top is 18. It doesn't matter what I substitute in for x, the top is always going to be 18. So nothing actually makes the top work out to 0. Bottom, however, we do have an x. It's an x minus 3, so in order to make the bottom 0, we'd have to substitute in a 3. Now, going to our number line, I'm going to go up here to do that. At 3. This function is going to be infinity. Why infinity? Because we have the bottom of the function equaling 0. We have something divided by 0 that was either undefined or infinity, whatever we chose to call it. Because we're going to be eventually dealing with the graphs of these functions, infinity works better. So now I'm going to pick two numbers on either side. I'll pick 0 and 4. Determine whether or not the function is positive or negative in each of those sections. So when I plug in 0, I get 18 over negative 27. Now, I can simplify that. I can divide both terms by 9. However, I don't need to. I'm not looking for the value of it, I'm looking for the sign of it. So we have 18, a positive, divided by negative 27, a negative. Positive divided by negative gives us a negative. So on the left of 3, that second derivative is negative. Do the same thing with 4. End up with 18 over 1. Again, simplifiable would turn into 18. But we don't need to go that far. We don't need to know the value. We just need to know the sign, which is positive. So now I can look and I can tell my concave up, concave down. Function's concave up from 3 to infinity. And concave down from negative infinity to 3. Points of inflection? Well, you might be tempted to say that there's one at 3. We have a sign change. Function goes from negative to positive. However, we also need that function being 0. Because the function's infinity, that's actually a vertical asymptote at that point. Vertical asymptote, if you remember, splits the function into 2 separate sections. We don't actually have a continuous function at 3. So since we don't have a continuous function, we can't have a point of inflection. So this function actually has no points of inflection.